Lesson 7, Interpreting the Execution Plans and Enhancements. So at the end of this lesson, you should be able to interpret execution plans. We slowly have been building on our knowledge on how to do that by viewing the execution plans and talking about them a little bit. And we're going to add some more details in that area. And then finally, we were going to have a look at the new feature, the adaptive optimization, and we want you to be able to discuss that. So here's our lesson agenda, and the first thing we're going to have a look at is interpreting a serial execution plan, which is really what we focus on in this course. So this is a model of the plan table, the way it gets generated when we place information in it. It has a couple of columns that are important. One is the ID of the step, which is the first column we have up here on the left in the gray box. And then we have the parent ID of the step. So at the top, we have something at the very beginning, ID 1, that has no parent, which is cardinal. We're going to build this into a tree structure that we show down at the bottom. So somebody has to be the top, the root, or the great-great-grandparent of everybody in the tree, if you look at it as an ancestral thing. Okay, so he acts as the root for the tree, the start of it. He also acts as the parent, and his children are at the next level down in the tree. So the next ID we have is number 2, and he is a parent of 1, which is so he's a child, his parent is 1. That means 2 is a child of the root. Okay, we scroll down a little further and we discover that 2 has some children because there are 1s that have parent ID of 2. So he's also a parent. From the root's perspective, he's the child of root, and he's this one on the left side. Because if there's more than one at a particular has the same parent, then we have a third column, the position, that says what order they're done in. And 2 is position 1. We also have another child of root, which is ID 7. He's in position 2. So it's kind of hard to read because they stuck the red line right in the middle of it. But that's life sometimes. So this parent has 2 children. Both of these have their own children. Okay, so we can just walk through. So 2 is a parent of 2. So 2 is this one on the left side. We put position 1 on the left and position 2 on the right when we actually build them. Okay, number 3 is a child of 2. Okay, so 2 is this one on the right, so it's a child. We have 2 of them that are child of 2. And so number 3 goes in the left. Okay, number 4, which is the second child, if I get it right, of 2. Number 4, second child of 2, goes in position 2, which is this position here. Okay. Now, if we look at the tree and look for an ID that has a parent of 3, we'll actually discover there is nobody that has a parent of 3. So that means 3 is actually the end of that side of the tree, so it acts as a leaf node. Okay, so 4 is the other side of this, and if we look, there are 2 children of 4. There are 2, so 5 and 6 are children of 4. 5 is in position 1, 6 is in position 2. This is position 1 over here. This will represent this leaf node, and then that would be 5. Number 6 would be in position 2. Okay, So we've done this side of the tree by the time we get to 6, because then we go to 7, and 7 is a child of 1, and it's in position 2, we already mentioned. So it's this guy over here, and for a couple of these, we put the big red, blue arrows and red arrows to show you which ones we're pointing to. The rest of them we can just follow down. Okay, number 7 has 2 children, 8 and 9. So 8 is in position 1, 9 is position 2, so this is position 1. This is position 2. Okay. The second one on the right, ID number 9, I can put my cursor somewhere near him, has a child which is 10, which is this one down here. So we formed a complete tree by following who my parent is, and then if there's more of us on the same level, what positions we are. Okay, so position 1, position 2, 1, 2, 1, 2. If there's only one, it will just say position 1. There's a couple of them like these, and these don't have any children, so the end of the tree. So there's a group of them that form the leaf that are the bottom level child. Okay, the one at the top is the root, the parent of the next level, which is the root of everything. And the way they designed this one, the way it flowed out, it's a 4-level tree structure that they've mapped out. Okay, and I joke this is a snowman in Ottawa in the wintertime, except for one time this year. We haven't had many snowstorms like that you couldn't see across the street or the end of the car, but we had one for about 15 minutes. A month or so ago. It was kind of surprising because the snow was getting ready to go, so it's still there, but different problem. Next up is interpreting the execution plans. How do we go through it? So we went in there and we got the execution plan for this query. What it is a join of the employee table to the department as an equal join with a not exist subquery that is using the salary grade column. And we're looking for the salary grade between a low salary and a high salary. We're looking for people that are not within the normal grade. They're outside of it. That's what we're looking for, the not exist qualifier. Okay, to do this query, it builds an execution plan. When we dump it with things like the DBMS_X plan, one of the display options, or use AutoTrace, it will use it as an indented table. When they go and express it as a tree table, then to actually follow the execution, you start at the top and you go left. So to do 1, which is a filter, we need to filter the 2 inputs for it. So it means we have to do the left-hand side and the right-hand side. So we go left first. To do this side, it's a nested loop. It has 2 inputs, one side and left side. We have to do this one first. Then we go back here and do this one to complete this. And then we go up here and we do this one. So you can follow up by just running around the outside is another way of looking at it. So we have to go to the bottom of the tree, do this first, do this. That allows us to complete that. But before we can do this, we got to do the one at the bottom. Feed it to this, does that. That allows us to complete both legs of this nested loop. And then we need to do the other one. So you just go down the left side, going around the outside shape of the tree, and look at the nodes that you go by. You do the one on the bottom first, and then you have to touch all of them and complete them, and then go up and down to complete this one, and then we're finally done. We got to do the left and the right-hand side before we complete it. To take a look at this as an indented tree structure, okay, what we're going to do is go down the most indented side of it, and we eventually find that this is an index access, okay, which is for the nested loop. These two are at the same level. Therefore, this nested loop, this is below it, so we take one side, okay, and do a full table scan on it, which is our full table scan of the employees table. So when they're at the same level and it's a nested loop or a hash join, you do the top, then the bottom. Okay, so we can go in and start a full table scan, retrieve a row, which this indicates here, using the full table scan from the employees table. Okay, then we need to take that row and we need to get a row from the other table, which is the department table. So we take the key value that we're joining on. In this case, it was the department number. So take the department number from the employee table for the first row and probe the index for that department number. Okay, if we get a match, we'll get one or more row IDs. Since this is a primary key, we expect exactly one row ID. It's a primary key on the foreign table. We expect one row in this case. And then you look up the row and join it with the table. If we probe the index and there are no rows returned, we just skip the row we just got in the full table scan and we read the next one. It's not part of the result set. There's no matching entry in the department table to join it with. In that case, it would be an employee with a null department. Okay, we didn't have anybody to join them with. And we just loop through and read each row and probe it and return the joining row if one exists to complete the join. When that's completed, we've done the nested loop. Now we need to filter it, and we're filtering it by this not exist subquery. So we need to process this sales grade table. To process that, we're just doing a full table scan on it. Okay, retrieve the rows, and for every row we retrieve, check if our employee meets the condition. Okay, that it's not acceptable. Okay, so the ones that don't fall within a good salary grade gets flagged and get outputted in the report. Now, they did put a hint on, but it's for the rule-based optimization, and the only reason why they put that in because they wanted to make sure it reproduced every time. And there was one way they found to reproduce it. Okay, execution plan interpretation. Okay, this time with this execution plan, we set the statistics level to all to get the extended statistics. Okay, then we're doing a join, and this is essentially the same one. And then we have a look at the execution plan. Okay, and now we're looking at the execution plan out of the cursor, what it's really, and what it is basically the same execution plan. But because we asked for statistics level all, and we asked for additional qualifiers, we said, give us the typical information. We want the execution plan basics, but we also want some IO stats, and we want the IO stats for the last run when we just run it, just to see how it ran. That will tell us the number of times we start each step. Okay, it will show you the number of rows, the actual rows we returned, and the number of buffers we had to touch. These are actual runtime statistics. A lot of times when you look at the display, you get the estimates only, but this one, because we asked for statistics level all in our session before we ran it, we actually get all the detailed runtime statistics. And what that is telling us is that for every time we join the table, for every row we join in the table, we started this full table scan once. We're just going to walk through the table and look at every row once. For every one of those, we had to probe the index. So there were 14 starts against the department table index probe. Okay, and it returned 14 row IDs that we could do. 14 times we found something. For the table access of the sales grid, we actually did that 12 times. Okay. And then the rows we actually returned, we got 12 rows from the full table scan of the sales grade. We got 14 rows from doing the index probe and looking them up in the index, and we joined them with 14 rows from the full table scan as an equal join. And these are the number of buffers each step we had to have a look at as we're going through the execution plan. So some of them had a relative, but we were doing full table scans on this one. We had to start it a number of times to find the match. Okay. We executed once for every result, and there was a couple of times we didn't. Okay. This is the different execution plan. Okay. We're joining 3 sets of tables, if I remember correctly. So we look at the from clause. We're joining the employee table with the new style join syntax to the department. The join condition is expressed in the on, which is the manager ID in the department table equals the employee ID in the employees table. We're just marking them as manager or something. And then we take the result set and do a natural join to the locations table. And then we have an additional filter on the locations table. We were looking for just the cities of Seattle, okay, at the time. So when we express it as a indented table, it shows it as a double nested loop, and we're using some indexes, okay. And we look at this flow chart, and it will show you the flow. We can also get it from the order we do it here. So the first thing it's going to execute is step 4, okay. This is the first one. We're going to do an index range scan on the locations table, which is this guy right here, because we found a filter that we can use it, so we wanted to use it to drive the table. And we forced a nested loop by asking it to do a nested loop on the D, that's the alias name, and a nested loop on the M table. Okay, so we do step 4, do a range scan on it. We're going to read through one side and probe the index. And this time we found an index to limit it, the location city index. Okay. Then we're going to pull up a row out of this if we find a row. Okay, and then we're going to probe the index on the department location index. It's on the department table, but on the location column. And we're going to join that in a nested loop. Okay, so follow this. They did 4, which was this one. Then they accessed the table, which is this step here. Getting kind of hard to follow them. Then we need to do the other side, do 5, which is, but before we can do that, we do 4. So we go to the bottom, do 6, which is an index range scan in department, as I mentioned, and then we do 5. That allows us to complete this. And then we're going to have to do 8 before we do 7. So it does the index unique scan on the employee ID. And then if it gets a matching row, we join it with the result of joining the row from this to produce the output set for this particular table. Execution plan number 3. Okay. This is a case we're joining A, B, and C. Okay, we're going to tell it to do a hash join, but we're going to swap the inputs, which means swap the order we actually do them, okay, the way we define it. Because we said do it in the order, but swap the inputs for C. So it switches C to the front and then puts the other one in the order they're listed, A and B. So in this case, following the chart, they'll do 3. To do one side of their hash join, do 4. And before they can do 4, they have to do 5 and 6. Take the result of that row join and join it with 3 to get a row from the whole result set. Looking at here, we can go down and find the most deeply indented one, which is this one. We're going to hash join 2 things. On the first side, which is table 3, because we swapped the inputs, what became last become first. For table C, which was our last one, it becomes first one. Build a hash table on this, table 3, okay, which is this here. Do the full table scan to build a hash table. We're going to join it with the results from this one. We're doing a hash join of that. To do that hash join, we have to do 5 first, do a full table scan on T1, because the rest of them we leave in order. We do them in the order up here because that's what the order hint tells us to do. Do T1 first, build a hash table on it, and then do a return a row, probe the hash table. If it joins, take that row, probe the hash table. If it matches, put the results in. If either probe we don't get a match, we're done. That row doesn't belong in this triple. When you read it from the SQL developer, it's actually pretty easy to follow. It actually gives you the ordering that you do it in. It says do 1 first, which is do a full table scan of this, build a hash table. Then it says do number 2, do a full table scan of this to build a hash table. Then do 3, retrieve a row from this, probe the hash table. If we get a match, join them together, and then feed it to the probe of the hash table we've already built on T3. If we get a match, it becomes join it, and it becomes part of our result. And then they eventually want to do a max value, so we'll have to do an aggregate. After we join all the rows, we'll have to find the maximum combination of A and B. The max values for the combination gives us the max of both A and B. So we just go through this. This makes it easy. When you're indenting it, you got to get used to the way you read it. As soon as you find the hash join, it does the first, then the second. To do the second, it's got to do this one. It has to do the first and the second. We can see that from the little chart. And this gives you their ID number and their ordering, which order they do them in. Execution plan interpretation number 4. So this one we gathered statistics on it. Again, we were doing a select of the order inventory where the warehouse ID equals 1. Okay, then after we execute it, we have a look at the execution plan in memory. We want all stats and we want the last one. We want to do a side-by-side comparison of the estimates to the actual rows we return to see if the estimates were actually accurate. So when we get the execution plan, it shows us the statement and it shows us our access path. So we're doing a range scan, and then a table access by row to solve the query. The index we're doing the range scan is in the inventory index, and then we're accessing the inventory table by row ID. We started each of these steps once. We were estimating we were going to return 124 rows. We returned 36. Estimates are estimates. Okay, we don't expect them to be right on. If I estimated 124 and I got 125, I'm okay. If I got 118, I'm okay. I estimated the actual rows I got was 36. Even if I double 36, it's only 72. We were off by more than 100%. That's a poor estimate. What it really tells me is this wasn't a very good estimate for some reason. Are my statistics valid? Even if the statistics are up to date, it still may give us a bad estimate because we may have not created a histogram. We may have just went out and used the normal distribution. If there's so many warehouses, it's 1 over the number of warehouses, okay, as the estimate. And it turned out that this is non-normally distributed. Some of them have lows, some of them have higher than what would normally be the normal distribution. So it probably says I should actually give it more information, give it a histogram. Next up, we want to talk about reading more complex execution plans. Okay, so now we have a complex query. It's actually against the data dictionary views. There's fun because some of them are very complex queries. They show you a little outline that they shrunk so you can't possibly read it. Now, how the heck do I start looking at this? It gets really tedious trying to find out what the most indented is. So their suggestion is collapse it. The one advantage in the GUI, you can collapse everything and then start expanding it a step at a time. Okay, and focus on the operations that consume the most resources. If I look at these two, one is a nested loop that takes 110. Okay, what is it? Well, I want my cost. It takes 1442. The whole view processing takes 1448. This takes 1339. What I would really like to do is find a difference, and if there isn't much, still just concentrate on the biggest one. If there's going to be some savings, it's going to be down the biggest side if I can find a better execute. And quite often that will lead you to the most expensive single step. And if I can improve that, I may have an opportunity, if I can figure out a way to improve that, to improve the whole execution plan. Or maybe if there's no way to improve it, we've got the best we can do. But at least we've got a way of exploring it and confirming if things look reasonable or not. Next up is the execution plan isn't everything. An execution plan alone cannot tell you whether the plan is good or not. For some queries, a full table scan may be horrible. For some, it may be the best execution plan available. Okay. We need additional testing and tuning. SQL Tuning Advisor, you can use from within SQL Developer, so it's available. You have to have access to Enterprise Manager to use the Access Advisor. Performance Analyst is usually used by the DBAs to do before and after looks at have the execution plans changed because of a proposed change to the database. Quite often we run it on a test database. SQL monitoring will allow you to do real-time monitoring of the big queries for the data reporting system, the data warehouse, and etc. Tracing will allow you to get the most detailed information about particular operations within the SQL statement. And it's a very simple information that we can glean a lot from. Okay, and adaptive SQL plans could give us the option to do a one-time change or adapt the plans into the future based on runtime statistics. So you really need to do additional testing. There's a little quiz for this one. We have this query, so we recognize this from the last example. And in this case, we have the estimates, because we just did it out of an explain plan view. Okay, or actually we did it with auto trace or we just ran select count to start to find out how many it has. Okay, so we found out for this predicate how many are returned just by doing a simple count with that predicate. We got 36. The optimizer estimated 124. So question 1, according to the execution plan, is the number of rows returned in step 2 quite accurate? Well, it estimated 124. We really returned 36. Sad to say it's not accurate. Okay. Question 2, what is the selectivity of the predicate and the computed cardinality? So there's 120 rows in the inventory table. There are 9 distinct values for the warehouse ID because that's our predicate. How the optimizer estimates take the number of distinct values if it doesn't have any histograms. Okay, 1 over 9 and multiply it by 112, and if you do the math, it comes to 124. So its estimates were based on a normal distribution, but it's not. This is a non-normal distribution. One got 36 because one is low, somebody's got to be high. Some of them are going to be higher than 124. Okay, so the optimizer has not made a good estimate. What we could do is to give it better information is a histogram on the warehouse ID to give it a better idea of the distribution, the number of inventory items that are in particular warehouses. And that will allow it to make a better estimate.